get it as close to the 60 gram limit as we could, because we believe that the mass would be the most important in determining, how much momentum the projectile would have and how well it would be able to penetrate the target. So, we wound up manufacturing the tip with a 0.025 inch end, and that was ultimately just for manufacturability, to make sure the tip wasn't too sharp and the tip was actually feasible to manufacture. And we made it out of tungsten heavy alloy. The 3.2 inch total length body was made out of aluminum 7075, which is an aircraft grade aluminum. And the fins are also attached to the body, made out of 7075. So for the assembly, we went through some iterations, obviously, over the course of our development, but as we were machining, we did come up with a final change. So our tip has the male component of the threading, and the body has the female component of the threading, and that threading is a 1/4-20. So after talking with the CNC operator that we were working with at Camel in order to manufacture our tip, we determined that the internal threading we initially decided to go with was not really feasible, and it was more practical to just put the male threading on the tip and the female threading on the body. And then initially, or over time working with Camel, we also modified our shoulders to help with the precision. So we sort of have two different shoulders in there to align the tip with the body and make sure that we get a flush surface overall once they're joined.
Now we'll move on to just a quick overview of our modeling and analysis. So our center of gravity is about 2.89 inches from our tip, and in this graphic you can see this shows pressure, and behind our projectile there's a low pressure region. And so from this simulation we were able to find our center of pressure, which was 4.478 inches from the tip. And that shows us that the center of pressure is more towards the fins, which is what we'd like to see. So this is more of a simulation of the pressure on the body. And so the fins and the tip carry most of the pressure. We want the fins to have most of the pressure, take most of that load, because that helps keep the projectile steady and aligned with its trajectory, and helps resist yaw and pitch movements, because it creates lift. Here is our launch deformation did in says structural. We did this using our aluminum 7075, and it shows pretty much what we would like to see is that most of our deformation is at the base of the projectile. And looking at our strain rate and our strength, we have decided that our material would withstand the launch.
So now moving on to our materials, we're first going to start at the nose. We wanted to have something that was strong, something that was dense, that could withstand an impact. So we first started out with pure tungsten, which had a good density and a good strength, but it turned out to be too expensive. So next we went to a tungsten carbide, but like the other group said, is very difficult to machine. So that left us with the tungsten heavy alloy, which had pretty good properties, with a density of 17.72 grams per centimeters cubed and 389 hardness per Néel number. Next, we move on to our body. We wanted something that was lightweight, something that was strong, something that could withstand the impact of launch. We looked at aluminum 6061, stainless steel, and aluminum 7075. 7075 had the best properties. It had low density and a high strength, but 775 is normally forged, which made it a question of how we're going to make this thing, and that we'll explain later. So, like I said, tungsten heavy alloy is strong and dense, and then the body is lightweight. We want the nose to be strong and dense so that it pushes center of gravity forward, and we want the body to be light, so that also pushes center of gravity towards the tip, and then having that will have the center of pressure towards the rear, and having center of gravity in front of the center of pressure, exactly what we want.
So going back to talking about the aluminum 775 body. But through our own research, we found a research paper about using a aluminum with nanoparticles, titanium carbide, and allow for better flowability of the material when investment casting aluminum 775. Aluminum 75 normally is a forged material, so to get the shape of the fins that we wanted to, we would like to either cast or 3D print it, and 7075, due to its forged properties, when it is casted or 3D printed, leads to hot cracking and micro repairs, so that would give us lower stability when we are actually launching our projectile. One of the previous groups mentioned aluminum silicon 3D print they found. We thought we wanted to maximize our stability, especially, and also minimize launch deformation, so that's why we decided to go with the aluminum 7075 body through the casting method. Above is a kind of the research paper's way of doing it. We mirrored this with camel. Basically, we would have a wax 3D print that we would pour plaster over and then remove any air bubbles through a vacuum chamber. It would then burn out the wax mold, leaving only the formation of the body, and then we would pour in our molten aluminum with which was 6061, with the nano-treated aluminum alloy, titanium carbide, which allow for flowability and to reduce the hot cracking, and then from there we would remove the plaster casing and machine down our part. So this is kind of talking about that hot cracking. This is what the research paper found. They did this with dog bones, and as you can see, that the normal 7075 casting has multiple hot cracks along like pressure points and sensitive areas, which would lead to, for our design, cracking along the fins. When added with the titanium carbide nanocomposite, they had 10 out of 10 dog bones successful, and it led to an overall better flowability of the material and better overall tensile strength, as you can see from the chart we got. This is our demonstration of it. This is kind of we couldn't follow it exactly due to the limitations of camel. So for the most part, the way we did it was we had the wax body printed with Formlabs Wax 40, which is a 3D printable wax material that will allow for better shaping of the mold when it is burned out and lead to less ash residue. So as you can see, the first picture is the burnout cycle, where we did multiple different temperature gradients to make sure that there was no ash left in the plaster mold. Then after that, we have the metal pour. Once the wax is gone and there's a recess, we would pour directly the aluminum mixed with the aluminum nanocomposites directly into the preheated mold at 450C. We melted the aluminum at approximately 800 and poured it at 900C to maximize flowability. And as you can see on the end is the final casted part. The main issue we found with this is that due to the research paper having they poured under vacuum at a negative 60 kilopascals, and so we were not able to replicate this at Camel due to the limitations of the furnaces. So that caused our fins not fully formed due to the surface tension and also air pockets where those fins are. We attempted we had multiple attempts at this where we increased pouring temperature, mold temperature, and then also added risers so that air would flow out of where the fins are and material would flow in. And in the end, we were not able to successfully get the fins to form. But from this, we were able to do analysis on the microstructures. As you can see above, the grains that form kind of around these little air pockets. The porosity, these little black spots are air pockets. The porosity is due to the lack of a vacuum chamber, which would have pulled these out. But you can also see these kind of little pink dots. This is the titanium carbide nanoparticles that basically are meant to form along the micrograin, the grain's growth to allow for the microstructure to be more stable and to reduce hot cracking. So basically, hot cracking, what happens is when aluminum is cooling, the grains are converging on each other, and enough stress builds up that they pop. And these titanium carbide nanoparticles are meant to kind of flow along the edges of microstructures and the grains to reduce that. And as we saw from our print, we didn't have any cracking, especially throughout our body, which meant the nanoparticles were successful in doing that. And conceptually this works, but we would have to redesign our mold and also maybe redesign the procedure for our pour. Here's a quick little video of us doing the pour. As you can see, there is Justin. He is going to place the 450 or 500C preheated mold in our sand just to catch any material that would have fallen out or from, and also to disperse the heat from the melt. That is me. I am currently grabbing the crucible with the 900C aluminum 7075. It's the nanoparticles, and we just pour it from that directly into our mold. If we were able to do this again, we would try to do this under vacuum to reduce the air pockets and also to make sure the fins would form, but due to the limitations here at Camel, we just were not able to do that and had to stick with what we got. But all in all, this was an incredible experience and it was a lot of fun doing it.
So in conclusion, a lot of our work was more material science based in order to figure out how to properly get the properties of aluminum 7075 through casting. I would say in that regard we were a success. We managed to get the nanoparticles and the titanium carbide to bond with the aluminum 6061 to give us similar properties. We did have complications, as Joey said, with our mold. We do believe that if we had access to a vacuum chamber that could withstand 900C, we would have been able to properly produce our fins and therefore have a fully functional projectile. We ended up using simpler geometries in order to machine our tungsten tip, as you can see here in this photo. And we used ANSYS in our design in order to properly see how it would function, and we believe we did pretty well. Any questions?
How did they word the research article under vacuum? I'm guessing there was a vacuum space.
I believe what they had, we didn't get to see the details of the board, but they had a lot smaller of a body and a lot less material. So I assume they had a furnace under vacuum that they were able to just open up, pour in through the vacuum, and then just let it sit. With how we had it, we only had access to our furnace was relatively small, so there's no way we could pour in it, as well as we only were able to pump argon through it and not have it completely vacuum sealed. So their furnace was able to be, it was at UC Berkeley and they had a lot more, funding for this, but their furnace was the vacuum itself and they were just able to put the mold in there, pour the material, and then let it sit.
Any other questions? Okay, thank you all.